This video is a short physics lesson answering the question, what's force? Forces are often described as something that pushes or pulls. Like this boy pushing on the bike, you could think of a jet engine producing thrust that pushes on the plane, a rocket engine produces thrust that pushes on the rocket, a ship's propeller produces thrust that pushes the ship through the water. For pulling, here's a tractor in a tractor pull competition. You can also think of the force of gravity pulling you against the floor or your chair right now. But that's not all. Oftentimes, forces work together. Two forces, three forces, even more, many forces can all be working on an object and producing something that you may not realize is being pushed and pulled at all, because it's in a state of constant motion, either constant rest or a constant velocity where it's moving at a steady speed and not changing direction. Forces are subtle and complex, so let's take a look at what we know about forces. Forces are vectors. They have a magnitude and a direction. That's how more than one force can work together and end up completely canceling out each other's effects. Their directions can point opposite each other. Forces can be long range, like gravity. Gravity between the sun and the earth holds the earth in orbit, and yet there's tremendous distance between the sun and the earth. Magnetism is another force that acts at a long range. Forces can also be due to contact between objects. If you actually push on an object, then you're producing a force through the contact of your body with the object. Forces can keep an object on a steady course, moving at constant speed with a constant direction. Forces could keep an object at rest, or forces can accelerate an object. To make sense of all this, it helps if we talk about Newton's three laws of motion. Sir Isaac Newton lived in England in the late 1600s and early 1700s. He was interested in what we now call chemistry and astronomy and physics and mathematics, basically any kind of science and much of math. He would have called himself a natural philosopher. He was curious about the natural world and the laws that governed the natural world. He made many, many very valuable discoveries for science. But in mechanics, the branch of physics, Newton's three laws of motion are fundamental, critical, and helpful in understanding how forces work. Often in textbooks, you'll find Newton's first law of motion stated as something like an object in motion will stay in motion and an object at rest will stay at rest unless a net external force acts upon it. Let's talk about what that really means. I always think of Newton's first law of motion as saying a net external force is required for acceleration. No acceleration, no net force. So when you consider an object, if the object's motion is changing, if it's speeding up, or if it's slowing down, or if it's changing direction at all, then there must be a net force, an overall force acting on it. If the velocity isn't changing, if it's not speeding up or slowing down and not changing its direction, or if it's at rest, then there could be lots of forces acting on the object, but they all balance each other out, so there's no net force. So we've been talking here about Newton's first law. So a pretty good example scenario to describe Newton's first law is driving a car on the highway. Now, as the car drives along, there are all kinds of forces acting on it. There's a long-range force between the car and the earth, pulling the car toward the center of the earth. The reason that the car doesn't move towards the center of the earth is because there's a force from the road that presses right back up on the car. If you're driving your car at a steady speed on the highway, you may have noticed that you have to keep your foot on the accelerator all the time, so you're constantly pushing the car forward. But you're going at a constant speed, And if you're not turning the wheel, then you're going at a constant velocity, so there must be something balancing that out. Well, it's mostly friction that's acting to keep your car, to slow it down, to keep it from accelerating. So even though there's lots and lots of forces acting on your car, they're all balancing each other out. And so there's no net force on your car when you're driving at a steady speed and in a straight line direction. Now, inside your car, there's all kinds of stuff going on too. There are bodies sitting on seats and springs in the seat pressing back. There are shocks and struts that are part of the car's suspension. Your foot presses on the pedal presses back on your foot. All those things going on inside of the car, those are internal forces, and they do not affect the overall motion of the vehicle. The only thing we consider for the motion of the vehicle are the external forces, and if they're all in balance, then it doesn't mean the car is at rest. It means that the car is moving at a constant velocity. If you want an acceleration, if you want to change the direction of the car, turn right, turn left, change lanes, if you want to speed up or slow down, then you need to produce an imbalance in those forces. You need that the force from the engine of the car accelerating overwhelms the force of friction, or you need the brakes of the car to produce even more friction to bring it to a stop, or the wheels of the car produce a friction force to the side which can make your car change directions. These are all examples of how Newton's first law governs the way objects move when forces act upon them. Newton's second law of motion gets specific about what kind of acceleration you could expect from a net force. Newton's second law of motion is just an equation. Begins with F. That stands for force. Force is equal to mass times acceleration. But in some ways, this is a really silly way to write it, because force isn't the result of acceleration. Force is the cause of acceleration. So let's do a little algebra. What we want to do is we want to take the force and divide by the mass. That tells me how much acceleration I can get out of a force. If the force is acting on a relatively small object, a small mass, I'll get a big acceleration. But if I have that same amount of force working on a big mass, I'll get a small acceleration. This is common sense, but it's telling us that there's a linear relationship between force and acceleration for an object, and it just depends on the object's mass. So what we've been talking about here is Newton's second law. Newton's third law in textbooks is often stated as, for every action there is an equal and opposite reaction, which I think is really unfortunate because it totally misses the point of Newton's third law. With all due respect to Newton, who was a genius, I think this could have been written a little better. So what Newton's third law is saying is that forces are shared equally between two objects. Forces can never be directed just from one object onto another. The force between the two objects acts equally on both, just in opposite directions. This is my interpretation of Newton's third law of motion. Why does the diver always fall toward the water? Well, the way we're all used to thinking about it is that Earth's gravity pulls the diver downward. Now, there's nothing wrong with that. It's true. Earth's gravity does pull the diver downward, although that's only half the story. According to Newton's third law, gravity between the Earth and the diver needs to pull on the Earth just as hard as it pulls on the diver. It acts both ways. At first, this seems to totally defy common sense. We see the diver fall toward the earth, not the earth leap up to meet the diver. So we need to think about the effect of force, which is acceleration. Newton's second law described how much acceleration we would get with a force. This force acting between the earth and the diver is the same magnitude each way. The masses of the two objects, the diver and the earth, well, they're different. The diver's mass is much smaller, and so the force produces a large acceleration in the diver. The Earth's mass is so large that that same force produces only a very, 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 very small acceleration. So small, we can't even measure it. So you might be thinking to yourself, how can we claim it even happens if we can't measure it? Well, that was just my example of the diver and the Earth. There are lots of everyday examples, pushes and pulls all around you, constantly, all day, every day, in which case it's actually easy to measure what we call the action-reaction pair of forces described by Newton's third law. Just to review the main points in this lesson, forces are vectors. They have magnitude and direction. Forces can be long range, gravity is an example of that, or contact forces, such as the force of one object pushing on another. From looking at Newton's three laws of motion, we learned three important things. First, that forces can be at work at objects even if they're in steady motion. Forces can be at work on objects at rest, or forces can be at work on objects with a changing motion or objects that are accelerating. In the case of steady motion or objects at rest, the forces are balanced. That direction part of the force vector works to cancel all the forces out, so you have a net zero force. Objects that are accelerating have a non-zero net force acting on them. Newton's second law told us that net force produces acceleration that's inversely proportional to the mass of an object. So if you have a constant force that acts on a low mass object, you will receive more acceleration from that force than if that same constant force acted on a higher mass object. Finally, Newton's third law explained that forces are always between objects, never from one object to another. The force that acts between the objects, it's really only one force, and so it's the same magnitude, but it's acting in opposite directions on the two objects that are sharing that force.